All right, so in this video, we're going to take a look at acceleration for the first time. So we're going to be building on some ideas that we've met in some of the previous videos. So let's start off by pulling out what those things are. So what I'd like to do is grab yourself a scrap piece of paper and see if you can answer the following three questions. This is the information we're going to rely on mostly as we work our way through this video. Okay, so let's see what we should have had these. Now we've had a chance to have a crack. So what is velocity? So first of all, velocity is short for instantaneous velocity, is the rate of change of displacement there, or we could phrase that as the gradient of a velocity of a displacement versus time graph. Those are the things we're going for. So you can see the keywords I would be looking for in here. And those are the things that are in the brackets. So when we see the word rate in physics, what does that indicate? So what I want you to think about when you see the word rate is the gradient of a graph with time on the x-axis. So we're going to come across a few of those. So when we say velocity is the rate of change of displacement, we mean that velocity is the gradient of a velocity displacement versus time graph. We're going to be saying acceleration is the rate of change of velocity, which means acceleration is the gradient of a velocity versus time graph. And then finally, what is the difference between average velocity and instantaneous velocity? We're going to meet average acceleration and instantaneous acceleration. So average velocity is the displacement divided by the time in which that occurs, whereas instantaneous is the rate of change of displacement. So average applies over a period of time. Instantaneous, as the name kind of implies, applies at a specific moment in time. Okay, so let's press straight into acceleration. We're going to meet several of these ideas you can see here as we go through. So let's start off with the more straightforward of them, looking at average acceleration first of all. And you can see this is in purple, so I'd like it to add it to the notes that we've been writing as we've worked our way through this video series. So average acceleration is the change of instantaneous velocity divided by the time taken for that change to occur. So you'll see I've expressed this in equation form. So if you see this delta symbol when we're working through physics, that means we're going to be talking about a change. That's the symbol that we use there. Quite often you'll see it written in a different form. You'll see it written in this equation you can see down below. And we use the symbol V to represent the final velocity of an object and the U to represent the initial velocity of object. So you'll see those fairly frequently. So it's worth remembering both of these forms of our equation. So that's our average acceleration. So let's move on to instantaneous acceleration, and we're going to write this in our notes as well, so we're clear on what that is. So instantaneous acceleration is the rate of change of instantaneous velocity, and what that means is the gradient of a velocity versus time graph. So that's often represented in this mathematical form here. So if we sketch a few graphs of velocity versus time, we can see in red that the gradient is increasing over time. It's getting steeper, which means acceleration is increasing. You can see blue, we've got constant acceleration because the gradient is constant. And in green, we've got decreasing acceleration because the gradient is getting less steep over time. So one important thing to flag up at this point is, although we've got increasing, constant or decreasing acceleration here, in all three of the scenarios, the velocity is clearly getting bigger. So decreasing acceleration doesn't mean slowing down. It's still getting faster. It's just the rate of increase is decreasing over time. Okay, so let's have a look at how we actually calculate acceleration, or specifically instantaneous acceleration. So the more straightforward way is if we've got a straight line graph of velocity versus time, because all we have to do is work out what the gradient of that line is. So here you can see we've got some points on our line. We need to work out the change in velocity divided by the change in time. Then we can figure out what our acceleration is. And you can see here acceleration is a positive number because this line is going upwards as we go increase in time. So that's a straight line graph. That's fairly straightforward. If we have a nonlinear graph, it becomes a little more complicated. And we can actually use this to illustrate nicely the difference between acceleration and average acceleration. So if we want to find acceleration, we at, say, this time here, we're going to have to draw a tangent to the graph at that point here. So this is what this line is called that we have drawn. It's a tangent to our graph. So let's work through these three stages. So first thing we're going to do is describe the acceleration over time. Well, the first thing I notice is the gradient is positive because it's going upwards as time increases, but the gradient is decreasing over time. So what that means is, so the acceleration is positive and decreasing over time. That's how we describe what we can see here. Maybe it's becoming constant at the end, but I don't think we have enough evidence to claim that just yet. So let's calculate the average acceleration over the first 10 seconds. So remember, average acceleration is change in velocity over the time that passed. So the change in velocity is, so it's 18 and it started at 0. And the time that's passed is 10 seconds. So we're just doing basically 18 over 10. So that's going to be plus 1.8 meters per second squared. Because we've done meters per second divided by seconds. And if we want to calculate the acceleration at 10, we need to find the gradient of our tangent, so m there, and that's going to be, we need to do the change in velocity, which is 23 minus 18, and we need to divide that by the change in time, which is 15 minus 10, so what's that? That's 5 over 5. Well, that worked out nicely. So that's plus 1 meter per second squared there. So we can see our acceleration here is actually lower than our average acceleration has been, which kind of makes sense because the acceleration to start with was quite a lot bigger. So that does make some sense. Okay, so what I'm going to do is I'm going to give you a couple of questions to have a go at on your own. So maybe on your scrap piece of paper. The first thing I like to do is compare and contrast average acceleration and instantaneous acceleration. And what that means is highlighting their similarities and differences. And then I'd like you to describe what's going on with the acceleration here and calculate the two forms of acceleration that we've met. So pause the video now and have a crack, and then we can review that at the end. All right, so let's review it. Now you've had a chance to have a go. I'll create a bit more space. So as I said, when you see this compare and contrast, what we want to do is we want to find the similarities and we want to find the differences. And I clearly can't spell similarities today. So what are some similarities? First of all, they are both vector quantities. So like velocity is a vector quantity. So the change in velocity is going to be a vector quantity, so that makes acceleration a vector quantity as well. And they are both measured in meters per second squared, or which is you often see me write that like this. So these are just two ways of writing the same thing. Differences, so average is measured over a period of time. Instantaneous is at one specific moment in time there. That would be, I think, a key difference between those two. So let's get on to looking at velocity time graphs, which is where acceleration really comes from. So let's give ourselves a bit more space. Okay, so the first thing I want to do is describe the acceleration shown by the graph. So the first thing I would notice about the gradient is it's negative because it's going downwards as time increases, and it's getting less steep over time. So that means the acceleration is negative and decreasing. There. Okay, so the first thing I want to do is calculate what the average acceleration is. So remember that average acceleration, we just need the change in velocity over the time taken. It finished going at 3 meters per second. It started going at 20, and that change occurred over a period of 10 seconds. So our change in velocity is minus 17, so that's going to be minus 1.7 meters per second squared. So it is indeed decreasing, it is indeed negative as we said it would be, which is promising. So let's calculate the acceleration. So we need to find the gradient. And the gradient of our tangent, that is. So let's do that. So this tangent, our change in v would be 3, well, what was it for? It was 10. And the time that's passed is 10 minus 4. So that gives us minus 7 over 6. And I can't do that in my head, so let's actually calculate that. Minus 7 over 6, giving you minus 1.2 meters per second squared. And does that make sense? Yeah, the acceleration was a much bigger negative number for most of this period of time, so it kind of makes sense that our final acceleration is smaller in magnitude than our average was. That looks good. Okay, so just to finish off, I want to show you what I would have added to my notes from watching this video. I think there's just 2 things that it's important to pick up. At this stage, I think I would add a couple of things in there that both of these are vector quantities. And maybe we could also add in that it's measured in meters per second squared. And I'll write the 2 different ways of expressing that. So let's have a look at the key thing in here. So we can see the average acceleration is the change in, so we can see change in the velocity of an object and divided by the time. So that gives us the keywords we're looking for there. And we can see that acceleration is actually short for instantaneous, and it's the rate of change of velocity. Or another way of expressing that is the gradient of a velocity versus time graph, which gives us that section there. So when we meet acceleration in the future, I'll give you these cues that we can see here to help you retrieve that information from your brain. Okay, so that's where we're going to finish off with this video. And what we'll start looking at next is the impact of acceleration on the velocity of an object, and using vector diagrams to figure out what the final velocity of an object is going to be based on the acceleration that it has experienced.